Assalamualaikum. How are you? I hope so you'll be fine. Today our topic is Young's double slit experiment. Before Thomas Young's, Huygens told us that life has particle nature and also has wave nature. But Huygens in his whole life can't prove that life has wave nature. In 1801, another young scientist came and he performed an experiment. With the help of that experiment, he proved that life has wave nature. So today our topic is that how life could interfere and how after the interference constructions and destructions could happen on the screen. So first of all, you should know that for this experiment the light should be monochromatic. Monochromatic. Light source should be coherent. Intensity should be almost equal or resemble each other. Intensity of light should be, let's suppose I have a source of light and this is the source of light, and we are putting a slit, and after this slit we are putting two other slits. After light passes through these slits, it do behave like a wave and diffraction do occurs here, and light will also pass through this in this way. And I am putting some kind of screen here. On this screen we will notice that there are some bright fringes and there are some dark fringes on the screen. So these bright fringes and these dark fringes shows us that here on the bright fringe constructive interference happened, and on the dark fringe destructive interference happens. So what actually this experiment is? We are moving towards the mathematical calculation for this experiment. By using the ray diagram, here is the ray diagram for this experiment. We need to put two slits. One is this, and we do name them as the A and the B here. Light is coming from here, and there is a screen in front of this scenario. If light is coming from here, according to the particle nature, this light should fall in front of the hole or orifice, and the light coming from here should fall on the in front of the second orifice. But it doesn't happen. We did notice that some portions are bright and some portions are dark. It means so construction and destructions in the waves happened. So first of all, we did notice that, let's suppose the distance from the screen to the slits is L, and this center is in between A and B is E, and at the front of the center, this point we will nominate as O. We did notice that at the center of the screen, bright fringe occurs. Light came over here, and both light waves constructively interferes here, and the bright fringe we will notice on this point. Let's suppose I give some kind of name to this point as P. Now the path difference from O to the P and B to the P, or A to the O and B to the O is AO minus BO is equals to the 0. There is no path difference. The path difference from the path difference comparatively A to B is equals to the 0. So bright fringe will occurs here, or we will see the bright fringe. It means so constructive interference happens here. If I want to deeply check out what happens at this point, or what will happen, let's suppose again here the bright fringe came across. When light from the point A will move here, and the light ray from the B will move here, both of them will constructively interfere. I take some kind of perpendicular here, and here this is the theta. This is the perpendicular, this second line, this will be 90 degree. We know that at the front of the theta is perpendicular, and opposite to the 90 is the hypotenuse, and this one will be base. So now I am talking about the path difference. So we know that if at this point one complete wave came here, one crust and one trough, then it means so the path difference is again in integral form, then it will be a bright fringe. So if I do put this triangle over here as it is like this. Here this is the 90, this is the theta, here is the point A, this is the point B, and we do give some kind of name to this point as we can say it as Q. So by the sine theta, we know that sine theta is equals to the perpendicular by hypotenuse. So in this context, in this triangle, what is the perpendicular? Perpendicular is from the point B to the point Q. So we can say it as BQ sine theta is equals to BQ. What is the hypotenuse here? Hypotenuse, that's the AB, and we do give some kind of name AB as D. This side is D. So this value will become, if I move this D to the opposite side of the equation, it will become D sine theta is equals to BQ. So what is BQ here? It's the path difference, and it is also called as the wavelength. If it's the complete wavelength, or in integral form 2 lambda, 3 lambda, 4 lambda, we will put here as lambda. It could be 1, 2, 3, 4. So generally I do use here as d sine theta equals to the m lambda. So whenever this equation will followed by the two paths of the light, or interference will be, the light interference will be d sine theta equals to m lambda. So if at this point this phenomena came over here, mean crust of, and second again here at the third crust came over here. So now it's the one complete lambda and 0.5 lambda. So this will not create here the bright fringe, it will be the dark fringe like this. So no light will come across here at the result. So the result will be d sine theta equals to the m from here 1 2 3 4 plus half wavelength means 1 by 2 lambda. So for destructive interference our equation will be d sine theta equals to m plus half lambda. After moving towards the, just note it if you want to note it. Now we will move towards the bright fringes and the where dark fringes will come across on the screen. We can find out with the method. Let's suppose that we will use for the bright fringe as bright fringe and dark fringe. For bright fringe we will use the formula that we have calculated as for constructive interference, and for dark fringe we will use the formula that we have calculated as m plus half lambda. So for bright fringe our formula was d sine theta is equals to m lambda. Okay, if our angle is very short angle, so on the side theta we can use as d tan theta equals to m lambda for very short angles. So we know that tan theta is equals to the perpendicular by base. And what is the, now we will include this triangle, and here it is the EO, and the distance from the bright fringe, let's suppose it's a bright fringe to the center of the screen, this will be nominated as Y. You can put any name here, and from the E to the O, that distance from the slits to the screen is L. So here perpendicular is, in this context, triangle EOP or POE. That will be, the perpendicular will be Y, this distance, and at the base from the E to the O, and that will be L. And after that it will come as perpendicular by hypotenuse. On the other line I am writing it down. DYL equals to m lambda. Now I have to find out the position, the bright fringe, and for bright fringe we have used the alphabet Y. Just take it out, L will go there, and it will be L m lambda, and D will divide here, Y equals to L m lambda by D. This formula will be used for the bright fringe. And for the dark fringe, we can use the same formula, but for complete calculation, dark fringe we know the formula for the destructive interference is d sine theta is equals to m plus 1 by 2 lambda. So again we will use the tan theta instead of the sine theta if the value of the angle is very small. d tan theta equals to m plus half lambda. So for again tan equals to the perpendicular by base equals to m plus half lambda, and perpendicular is again the y, dy by what is the base here? Base is the from the point E to the O is L, that equals to m plus 1 by 2 lambda. Take it out, it will become, L will go there, so m plus 1 by 2 L lambda, we will divide here, and now our answer will be y equals to m plus half L lambda divided by d. This is calculated for the dark fringe. You can put the values and find out the where is the either that is dark fringe or either that is the bright fringe. After calculating dark and bright fringe, we will find out the distance between the dark and bright fringes. Let's suppose it's the bright fringe, and here it is the bright fringe. So after doing this, I am making it for the clear calculations and clear understanding. The distance from one bright fringe to another bright fringe and the distance from one dark fringe to the other dark fringe. So it is called as the fringe spacing. It is called as the fringe spacing. Fringe spacing. For fringe spacing, it's the change in y, the distance from the center to the fringe, that is either bright or dark. What is the formula? Let's suppose the formula for the change in the perpendicular is equals to the del y equals to ym plus 1 minus ym. So what will be the ym? Ym will be equals to the L m lambda by d, and for the ym plus 1 it will be equals to the m plus 1 by 2 L lambda by d. So we have to put these values in this equation. Then del y will be equals to, what is the value for y? It's the value for y m plus 1, m plus half by d and minus what is the value L m lambda by d. So after multiplication, sorry to say that 1 by 2 doesn't comes here, it's only m plus 1, sorry for that. First we will multiply both of them, the result will be m L lambda by d. It will again multiplied by 1 L lambda by d, and what's left L m lambda by d. So it's the ml lambda, it's also the ml lambda in minus, so both of these will be cancelled out and our result will be L lambda by d. L lambda by d. So it means so that the distance between the fringes is directly proportional. I am writing here, the distance between the fringes is equals to the, is directly proportional to the, if we increase the distance from the slit to the screen, y is directly proportional to the L. L is the distance from slit to the screen, and y is also directly proportional to the lambda. If we are taking a wave that has the long wavelength or the greater lambda, this distance, the spacing between the fringes will be also large. But y is inversely proportional to the distance between the fringes, distance between the slits, distance between the slits. So Thomas in 1801 proved this whole scenario by experiment, and experimentally proved that the wave has, the light has the wave nature. Thank you so much.